Welcome to the Real Python Podcast. This is episode 257. How does the performance of an algorithm hold up when you put it into a realistic context? Where might Python code defy big O notation expectations when using a profiler? Christopher Trudeau is back on the show this week, bringing another batch of PyCoder's weekly articles and projects. Christopher shares an article about why real-world performance often defies big O expectations. The piece starts with a task coded in Go and then optimized from ON squared to ON. Can an interpreted language like Python compete with a compiled language? Profiling the performance of both versions provides some interesting results. We also share several other articles and projects from the Python community, including a news roundup, the fastest way to detect a vowel in a string, whether Python dictionaries are ordered data structures, an overview of Python's enum module, a Python client library for Google Data Commons, and a project to convert plain ASCII to smart punctuation. All right, let's get started. The Real Python Podcast is a weekly conversation about using Python in the real world. My name is Christopher Bailey, your host. Each week, we feature interviews with experts in the community and discussions about the topics, articles, and courses found at realpython.com. After the podcast, join us and learn real-world Python skills with a community of experts at realpython.com. Hey, Christopher. Welcome back.
Hey there.
We got a whole bunch of stuff this week. As usual, we got some releases, a little bit of news, several topics. We're going to bypass the discussion this week, but we do have a couple interesting projects. So you ready to dig in?
All set.
All right, cool. Let's start with those releases.
Yeah, like you said, summer solstice is past, and so the news is starting to slow down, but that doesn't stop people from contributing to open source. So there you go.
Yeah.
First off, the Rust-based linter ruff has reached version 0.12. This release is more version aware. So if you had a match pattern that you were trying to use before Python 3.10, it'll let you know. Next is the Web App Toolkit Streamlit. It's released version 1.46. Looks like a lot of small changes, particularly to the advanced layouts capabilities. And third is the XML parser lxml, which just released version 6. This has a mix of additions, including several performance improvements and some better type hinting.
Nice.
One other piece of news, it's once again time for the Python Software Foundation board elections. Nominations for board positions are due by July 29th, so we've got about a month, with the actual vote happening in September. There are a few milestone dates in between, so check out the link in the show notes for details. I don't know about you, but I vote for margaritas on the deck.
That sounds nice. All right. Let's dig into topics here. I have a couple that are kind of data type based. The first one is from Real Python team member and previous guest Stephen Gruppetta. It's on his blog, which is titled The Python Coding Stack. And this one's titled, Are Python Dictionaries Ordered Data Structures? And isn't there a thing about articles that ask a question that the answer is always no?
What is it? Bettridge is something? Hold on, I'll look it up.
Law, you can look it up.
Bettridge.
Anyway, in this case, as the subtitle says, it's nuanced. So some data structures are ordered in Python. Lists, tuples, strings, and they're typically called a sequence. You can literally use an index inside those to find the number of a very specific element and located inside there. But dictionaries behave differently. That's the whole idea of having a key and a value. And so Stephen's piece starts with a little bit of history. Before Python 3.6, it was clear that dictionaries weren't ordered. If you created a dictionary, even after creating it, when you went to look at it by printing it out, it might have a different order than what you had entered in when you created it. Python 3.6, which is rather old now. In fact, I think it is no longer supported. Is that right?
2 versions passed. 3.6 and 3.7 are both dead. We're down to 3.8.
Okay. Wow. Okay. So it was the first one that I started to use regularly. So, and I'm a newish Python user comparatively. 3.6 changed how dictionaries were implemented in the main Python interpreter, CPython. And as a result, Python dictionaries now will maintain the order of insertion of key value pairs. And so, key idea here, no pun intended, it's going to maintain the order of insertion. So, like where things are being inserted into it. This was an implementation detail in 3.6, but in 3.7, this became part of the Python language specification. So from that point on until something changes, order of insertion is guaranteed. But there's still some quirks there. Stephen uses, as an example, a queue of people, basically people lining up. Can either use queue or line?
It's usually line, but there's enough Brits around, we know what it is.
Yeah, okay. So you got your queue of people with their names as keys and then empty lists as the values for each. The idea he had in there is that the values would be like they're lining up for a store that's going to open, and the list will have their future purchases inside them, but currently they're empty. So are waiting to get into that store. If you compare two dictionaries, which have the same keys and values, but are, as you create them, in a different order, for whatever reason, if you do a comparison of them, say you name one queue and the next one you name another queue and you have the names in slightly different order as far as the keys. If you do that comparison, equals, it will evaluate to being true, but they're not in the same order. So they have the same keys, the same values. This is sufficient to make them be equal. And so Stephen goes on through with this comparison, talking about sequence types. If you create two lists of, say, you just use the names in this particular case as objects in your list, but you put them in a different order and then you do a comparison for lists, they will not be equal. The order of the items is a fundamental characteristic of lists. And this is the same for other items I mentioned before, which we typically call sequences, tuples, strings. And so, again, the key phrase in the documentation for Python dictionaries is dictionaries preserve the order of insertion. They are not ordered in the same way as a sequence. Before this existed in Python, if you wanted something that was ordered, you could use something from the collections module and you could import an ordered dict. And in this particular case, if you create two ordered dictionaries or ordered dicts and then do the same thing where you do your key value pairs and compare them, it would then not evaluate as equal when comparing them because they are not in the same order. So it's something that's, it's kind of interesting feature and something that if you look at the two types, if you are really concerned about having the order of the dictionary be important, I'm going to provide you more details. You can kind of dive into them. We have an entire course comparing them, ordered dict versus dict in Python. Which one should you choose the right tool for the job? In a lot of cases, again, the difference is minor, but it's something you might think about depending on what you're trying to create. And then also include a link to collections, container data types that's in the documentation for Python that'll give you an idea of the ordered dict objects there. Thanks, Stephen, for this. Again, did you find the?
It is. It's Bettridge's law, named after Ian Bettridge, who was a British technology journalist.
So are Python dictionaries ordered data structures? No. All right.
To go along with that, my wife and I are watching an old British cop show, and their photo lineup isn't a queue, it's a parade, which I thought was very fancy.
Oh, yeah. Okay.
They have photo parades. I don't know if they still use that term. This is like a 30-year-old show, but I found it amusing.
Number 3, step forward.
Exactly. Turn to the left.
All right. What do you got for us next?
My first article this week is called The Fastest Way to Detect a Vowel in a String, and it's by Austin Henley. The title's more or less self-explanatory. Austin goes through 11 different ways to search for a vowel in a string and measures the performance of each. So first off, the rules of the game. The function that does the work takes a string as an argument, the thing you're looking for the vowel in, and only returns a Boolean. So it's true if the string contains an English vowel and is false otherwise. Before I go on, I have a little challenge for you. Pause the podcast, jot down as many different ways you can think of to do this, and then when you're ready, you can compare your list against the one Austin came up with. I guarantee you won't come up with at least one of them. We'll get there. So, welcome back, if you paused. Method 1 is sort of an old school, almost C-style loop going through a character at a time. It invokes lower on the string, then checks each character against the string A, E, I, O, U. I guess we're not doing sometimes Y. He also does a variation on this without the call to lower, since that creates a copy of the string, and that might actually have an expense to it. Method 2 takes this C-style one step further and skips using the call to in and just builds a compound if statement for each letter. Method 3 uses a nested loop. The outside loop is for the string argument, and the inside loop is for the string containing vowels in both cases. So that's kind of implementing the in manually. Method 4 uses sets, creates a set based on the string and another set based on the vowels in both cases, and then the function then returns the intersection of the two sets. Austin takes a little tangent here to talk about big O notation, and that this is order n. I'm only mentioning this because I'm foreshadowing. If all that is gibberish to you, put a pin in it like Arnold, I'll be back. Right. Method 5, a generator expression. This uses the built-in any method with a generator expression inside that loops through a string of both cases of vowels and calls in on the string argument. Method 6 goes old school and writes a recursive function, peeling off the first letter, then recursing on a slice of the list. Almost there. Method 7 uses the regex search method wrapped in a cast to Boolean. Method 8 also uses regex, but instead of using the search, it uses sub, substituting any vowel with an empty string, and then it takes the length of the original and the end result, and if they're the same, there were no vowels. Method 9 is where he starts to run out of steam or gets more creative, depending on how you want to take it. He tries the built-in filter method with a lambda with the vowels. This one is unlikely to be performant. It will get worse as the string argument gets longer. It has no short circuit evaluation. It has to go through everything. And then method 10 is a variation on method 9 using map instead of filter. And for the all-out, this is kind of crazy prize, method 11 was suggested to him by one of his students. It maps each letter to a unique prime number, calculates the product of the character's primes, then checks the GCD of the product of vowel primes against the original number. If the GCD is bigger than 1, then the two numbers share a prime, so there was a vowel inside. There's also a crossed out method 12 that mumbles something threads, but he rather wisely decided not to go into that. So with all these methods in place, now it's time to test performance.
Can I pause you briefly?
Of course, yes, please.
What's GCD? I'm sorry.
Greatest common divisor. It's
right.
Okay. Sorry. It's basically when you look for common factors between two numbers.
Right. So you're going to find the prime there. Okay.
So if it's shared primes, then you'd end up with the same greatest common factor. If the two numbers shared a factor. Yeah, is essentially what's going on there. Yeah. Where was I? So to test this, he generated 2,000 random strings, half with and half without vowels, then ran each of the 11 methods against each of these strings 5 times, then did this 3 times each. I did not quite understand why, but I'm assuming he's just looping to get good numbers. And then he reported what the fastest total time was. So on a string length of 10, there's roughly an order of magnitude between the best and the worst. The best being the loop that uses the in to check membership. So the simple one that everyone would kind of go to was actually fastest.
It's got a nice short circuit built into it.
And the worst, not surprisingly, was the prime number beast.
Yeah.
One thing of interest is that the nested loop, which in theory is doing the same thing as the in variation, was third worst. So it's way down the list. And this kind of shows you the difference between pure Python code and when Python dips into C under the covers. So by using in, it's kind of doing the same thing, but because it's doing down in the compiled portion, you've got a much bigger performance boost. And we'll come back to that later. So he then did all of this testing again with strings of length 100, 1,000, and 10,000. And most of the methods had proportional execution time. So as the string went up by a factor of 10, so did the runtime. This feels somewhat counterintuitive to me. Anything with a short circuit design, I would have thought should cap out when it hits the first vowel. And as the set of characters is limited and randomness should evenly distribute the vowels, I would have expected there to be a cost cap around the size of the set of characters. I suspect that the cost of playing with the string is more expensive than the cost of the searching, and so my guess is wrong. And that, boys and girls, is why you should never guess about performance, but you should always measure. Put a pin in that one. We'll come back to that as well. So anyhow, a couple of other interesting results. As the string gets bigger, the regex performance tanks. So much so that if you graph the performance, he's got a chart in the article, its line crosses the prime mechanism line around the 200 length string point. So a little more expectantly, the recursive method also doesn't finish for all versions. Somewhere around length 1,000, it just borks, and that's because you run out of stack space. So to turn all this on its head, he does one more run where the strings with vowels only have vowels in the last 10%. So everything is backloaded, which means essentially you have to go through most of the string in order to find the vowels. The performance changes once more, with regexes now coming out on top this time. So it shifts. The good news is the prime number mechanism is very consistent. The bad news is it takes over 200 seconds when the next worst is only takes 10. So yeah, consistency isn't always the thing you're aiming for. The article goes on to dissect the underlying bytecode in a couple of the versions and gives explanations for some of the performance characteristics that I've mentioned. Like I said, best to test when performance is concerned. Your situation might be unpredictable. That's more foreshadowing. This was a great article by Austin, and there's a lot to dig your teeth into here. So if you want to better understand how coding choices impact the speed of generating your results, it's worth taking a look at.
Yeah, why you should know some of the built-in functions.
Yes.
that take advantage of C. Yeah,
yes.
That's great. All right, well, my next one is also kind of dealing with some nice built-in stuff inside of Python. This is from Rodrigo, who I had on the show recently. He's also making video courses for us at Real Python here, which is great. And it was really fun talking to him about teaching Python. So if you want to learn a little more about that, and he also has a really fantastic blog. And his blog, the website is maths.pp. The joke was that it was maths plus, and maths with an S is, basically everybody but us US, and I guess Canadians too, right? You guys call it math.
No,
right?
we don't pluralize it.
Yeah. Okay. All right. So it's, I guess
our English is based on your television. So we,
yeah, since we don't say it,
we do silent things like put U's in the words, but the actual linguistic stuff tends to mimic your Midwest.
You have much more interesting colors than
that's right. So. Yes, we see extra colors.
All right. So this one is kind of a series that he does about modules. And this is a module overview of the enum module. He's been writing about built-in modules for a while. And I feel like this one lands kind of in this intermediate developer path. As you learn the basics and you kind of get into the state of like running a few of your own applications, you might start to look at the idea of like refactoring your code, ways that you could make it more extensible, and kind of come into some other ideas. It's something that I went into really deep with Dane Hillard back in episode 49. He had written a book titled Practices of the Python Pro, and we discussed this idea of extensibility and looking at ways to optimize your code and make it more reusable in some ways. And generally defining and using constants is something that is kind of a little more common in other languages. Part of the whole dynamic typing inside of Python is something that a lot of people don't learn these ideas and concepts, but definitely other languages, this is something that's like core and taught really early in the basics, I feel like. So there are these naming standards. So if you want to use constants, there are naming standards for doing this and best practices for how you should do this in your code. And the enum module takes this idea of constants a little bit further. The module is used to create enumerations and make it easier to work with groups of related constant values. And so these are things that you're going to reference in your code later that you want to have easy access to. And there's a variety of reasons. And he goes through lots of code examples inside this. It's a rather long exploration, so I'm not going to go too deep into all of the different things that are in there, and also provide some additional resources if you want to continue to look at it. I'll start with just the first section, which is just how do you create enumerations with enum. He starts with an example using temperature conversion. And in this particular case, I know for myself, having to type out Celsius or worse, Fahrenheit each time is going to get messy and prone to typos. It's like, where's that H go? Or H's. So he calls the process of typing in the values as strings loose string values, which I thought was an interesting term. By defining enums, you get this benefit that your IDE will now have the ability to auto-complete that. You can kind of use dot notation, which is really nice. And enumerations let you kind of group related values together. And it also kind of acts as a form of documentation, which is nice. It gives you all the valid values that are available in a nice readable way. So he shows the code of setting this up with the temperature enum, importing from enum, import enum with a capital E for the second one, and creating a class, in this case, temp unit, and then it's building on top of the enum class. And then you're defining Celsius and you're defining Fahrenheit. He shares how you can manually type in the values in the enumeration. And going beyond the temperature one, he goes into this idea of like, well, what if you have a large collection, something a little bit bigger where you might be having to constantly add numbers for something, like maybe you want to list out the weekdays or something like that. So you're saying Sunday equals 1 and Monday equals 2, and you're, again, typing every value as you go. There's a feature that's kind of interesting there. It's sort of a shortcut in the numbering process that I wasn't aware of, where you can actually use a shortcut value of auto, and it will actually add the numbers automatically, which is kind of interesting. So in the case of 7 values, it's maybe not that useful, but if you're enumerating 20 or something more, or again, in the case that if you need to update this, or you might accidentally skip a value or repeat a value or something like that, delete or reorder, auto would actually help you with that by automatically numbering them, which I thought was an interesting feature of the enumeration module. Enumerations provide some extra features. There's a class of an enumeration that can be queried for the number of members that are in it and contains. You can iterate over it to check all the members and their values. Again, the article continues to dig way deeper into all this stuff, much more specific and specialized enumeration types, string enumerations, integers, flags, enumerations with aliases, flags with aliases, and all these are detailed out with chunks of code explaining all of them. And then some additional convenience tools to do things like check value uniqueness. Python 3.11 added a decorator. The enum module can verify things like what's unique. Are these values continuous? What are the named flags? And again, he goes into all the examples kind of showing off that stuff. It's a nice deep dive into the enum module. And again, I like that he has the code examples throughout. This is, again, something he likes to do, is go through these modules and kind of explore them. I think it's a really great way to learn more about this stuff, in his case, by writing about them, but I think you can kind of follow along as he does his research. So I'll include not only his article, a link to that, but we have on Real Python a tutorial titled Build Enumerations of Constants with Python's enum, and then a video course, which I probably will make the spotlight this week, covering there. Is this something that you use in your code, like as you have gotten further into developing?
Yeah, I try to. Enum's a late addition to Python. Like I think it popped up in like 3.5 or 3.6, something like that. So I actually had a enum, like a custom enum class in one of my utility libraries that I used myself and then had to deprecate for this. I find it useful for constants. The idea of groupings of constants is really, really common when you're mucking around with like databases. So if you've got a property of, let's say, eye color, and there's only supposed to be whatever it is, 4 or 5 choices, and what you're going to store in the database is like a short form of that, right? So B for blue, G for green, R for brown, whatever it is, days of the week, same kind of thing. So rather than take up extra space in the database, you would just store that single letter. And so the enum lets you go back and forth.
Right.
It does bring me to one caution with the auto feature. If your code is self-contained, it doesn't matter. But if you're storing the value, I tend to avoid auto.
Okay.
And the reason for that is, let's say it's, gives you, you've got 5 things and it goes 1, 2, 3, 4, 5. And then for whatever reason, you stick something in the middle. Well, now it's 1 through 6, but the numbers won't match to the old thing. And if you've got it stored in the database,
you've run the code before and it's in the database. Okay.
Then your 3 is your 4 is no longer what 4 used to be, and that can muck things up.
Okay.
So I tend to be very, particularly with the database type stuff, I tend to try and hold on to it. And that might mean you end up with gaps in your numbers if you take something out, but then at least you've got backward compatibility without having to write a script to fix the database. So just a word of warning, depending on how you're using it. Yeah.
It's time to shine a spotlight on another RealPython video course. It's one I mentioned in our discussion about enumerations in Python. Enums enable you to create sets of logically related constants that you can access through the enumeration itself. If you're familiar with enums from other languages and wish to use them in Python, or if you simply want to learn how to work with enumerations, then this video course is designed for you. And the course is titled Building Enumerations with Python's Enum. And it's based on an article by core RealPython team member Leodanis Pozo Ramos. In the course, Darren Jones takes you through how to create enumerations of constants using Python's enum class, how to interact with enumerations and their members within Python, and customize enumeration classes by adding new functionalities, apply practical examples to gain a deeper understanding of the benefits of using enumerations. Whether you're looking to categorize data within your code or refactor your application to make it more extensible, I think learning about enumerations in Python is a worthy investment of your time. RealPython video courses are broken into easily consumable sections, and where needed include code examples for the techniques shown. All lessons have a transcript, including closed captions. Check out the video course. You can find a link in the show notes, or you can find it using the enhanced search tool on realpython.com. So this is what you were building up to, something that I've thought about, but I haven't explored as deeply. Again, my lack of background in computer science is one of these things where I kind of scratch my head about the focus on it of sort of performance.
Yeah, so this article's called Oh No You Didn't by Mr. Shiny 608, who in real life goes by Timothy Brooks, but I'm going to stick with Mr. Shiny because that's fun.
Yeah.
The oh no in the title is written as if it was big O notationed to give you a better hint as to what this topic is. If you're not familiar, big O notation is a way of thinking about the computational complexity of an algorithm. It comes from math. In math, it's used to describe the limiting behavior of a function. So that means as the function heads towards infinity, what happens with the result? It's denoted by a capital O, being short for order, actually short for a German word that roughly translates to order, but that's good enough. And then you get, like with a function, you get parentheses. So it looks like a function call. And then what goes inside of the parentheses is something about the complexity. So O1, so it's O parentheses 1. This is sometimes pronounced as O1 or order 1. That means the computation runs in constant time. Now, it doesn't care about what constant time. It could take 1,000,000 years, but if it's always 1,000,000 years, regardless of how big the chunk of data is, then we just simplify that to order 1. That prime thing before might have been close to this, right? Because it was giving 200 seconds every single time. Yeah. That doesn't mean it's faster, but it's consistent. And really what this comes down to is how does it change depending on how much data you give it? So ON means proportional to the data. So the more you give it data, N items of data, the longer it takes, scaling with the amount of data.
Okay.
So because this idea talks about limits, I could have a constant time algorithm that runs slower than an order n algorithm for some size of data, right? So I might be able to run through 100 things faster than my constant time. Order n isn't always faster, but as we approach infinity, order n should take longer. And, eventually your performance curves will cross. And that's kind of the point of Mr. Shiny's article, actually. So performance style questions are somewhat common in interviews, and the article relates the tale of getting one such question. He was given 2 lists of unique numbers and a target, and then he had to find the indexes of the numbers from each list such that when the numbers were summed, they equaled the target. So if I have 1, 2, 3, and 1, 2, 3 is 2 lists, and the answer is 4, then I need to find the 2 and the 2. And if the answer is -1, then there's nothing that can sum it, and there's no answer, essentially is how it works. So Mr. Shiny wrote some code with 2 for loops as an answer to the interview question. And in fact, the first couple of approaches in the article are actually in Golang, but it's readable enough. It's, a loop is a loop. It looks kind of like Python. And it loops over the first list, and then the inner loop loops over the second, and then it just checks the sum against the target. So this is a typical answer you would give, and it's sort of kind of the naive approach. And if we relate this back to our 11 methods to find vowels, this is equal to our sort of early ones on.
Yeah.
So as often happens, the purpose for asking this kind of question in an interview isn't, oh, do you know basic looping? It's to try and have a bigger conversation. And the follow-up question was, can you make this faster? And Mr. Shiny's answer was basically no. And that's not technically correct because of all this big O conversation. So that double loop approach is an n squared problem because you've got the outer loop being an n times the inner loop being an n. So it's n times n, giving you n squared, which means the limit approach is the square of the size of the data. And that, in theory, is considered bad. But there's a difference between theory and practice. And big O often gets mistaken for measuring speed, when what it does is it expresses how performance degrades as the size of the data increases. And constants are more or less ignored. So unless you're dealing with really large amounts of data, sometimes this really doesn't matter. So,
right.
An alternative implementation of this sums problem is to use a hash. You stick one of the sets of numbers, one of the lists, into a hash, then loop over the other set. You subtract the target from the item in the loop that you're looping over, and then check if the difference is in the hash. In theory, this should be better because hash lookups are constant in time, theoretically. So you've got an outer loop, and then you've got a constant inside of that outer loop, which makes this order n, which is better than order n squared. The important part in this last sentence is theoretically. So what Mr. Shiny then did was actually test all of this out. He profiled the nested loop using a target that wasn't achievable, meaning the algorithm has to go through both lists of numbers completely. So that's worst case scenario, no shortcuts here. And then he graphed the nested loops, and you get a nice little n square pattern. You got the little curve that looks like an n square, which is kind of what you expect. Then he goes and does the hash version, and that wasn't so helpful. So instead of getting that straight ON line, which should be a straight line, he got a staircase. And the staircase is not just a staircase, but each step of the staircase was higher than the previous one. So it's just getting worse. And for most of the time, it's actually performing worse than that order n curve. And the problem with reality is it contains pesky little things like memory allocation. So when you reach the currently allocated limit of a hash, the map has to be grown, and that requires memory allocation. And depending on your hash algorithm, it might also require copying data as well, which is expensive. And this is why he got those staircases, because you get nice little performance for a little bit, then you hit the hash limit, and then it had to allocate it, and you jump up at the cost of that. So at about the data length of 500, the bad n-squared algorithm actually outperforms the good hash one. So unless you're doing this with really large chunks of data, then the so-called worst algorithm is the better one. So context matters when going from theory to practice. So far, I've only got through about half the article.
Yeah.
This is a Python podcast, you might remember. So the second half of the article is where the Python kicks in. So out of curiosity, Mr. Shiny went and wanted to see how interpreted Python would do against compiled Go. The nested loops version behaved in a predictable fashion. You still got that n squared curve. It was about 4 times slower than Go, and that's not really surprising. What was surprising was the hash version in Python not only kept up with the Go equivalent, but it also showed the originally predicted straight line, no staircase. And this is because of how Python implements the hash. Python's dict is the hash. It's heavily optimized because almost everything in Python is an object.
Yeah.
It's been a while since we've done that. And underlying all that object stuff really is just a bunch of dictionaries that's keeping key value pairs of the attributes. So they have optimized the heck out of dict and it's compiled code underneath. So although Python is slower, it's actually keeping pace with Go here because the significant percent of the time of this program is being down at the dict level, and Python is matching Go and performing in a way that is we wouldn't have predicted. So to circle back, 2 lessons. First, theory is great, but depending on the context, theoretical might actually get beat out by practical. And second, I'll echo the lesson from the other article, which is you really have to measure to know what performance will be. Even experienced coders tend to suck at predicting these things. And so don't guess, measure.
Can I take you all the way back to the top where
Sure.
you're doing O and then parentheses N?
Yeah. So the N, it's so you think of it as a function. The N is the thing inside of the parentheses is the thing you're handing it.
Okay.
So when it's 1, I'm handing it a constant time. When I'm handing it N, I am doing N amounts of data, right?
Okay.
And so for an order N function, if I pass it 3 and that takes 3 seconds, then if I pass it 6, I would expect it to take 6 seconds.
Okay. So think of it as an actual like function, and then the amount of data that it's being handed as a parameter or whatever.
And because this really comes back to limit theory in math, N at any point in time can be substituted for infinity. And what does that curve look like?
Okay.
Right. And then, so, just to keep on with the example. So if it's order N squared, then passing in 3 items taking 3 seconds, passing in 6 items would take 9 seconds because you're doubling the size of the set, but you're squaring the amount of work that has to be done. And the holy grail of algorithms in computing tend to be like log performance if you can't get constant time. So if you look at things like tree algorithms, B trees, and things like that databases use, it's in order to move. So a table scan is order N because you have to go through every row in the database.
Right.
And what indexes do is give you cheat codes for not having to do that. And they do that through trees. And you can search trees. So you can split it down into a binary search and it gets you log-based performance, which is better than a straight line, right?
Right. Yeah. Or squaring.
Yeah. Much better than squaring. Yeah. Yes. That's right. Yeah.
So your example of 3, just to clarify, that would actually go to 9. Is that right? Because we squaring it?
Well,
I think you said 6.
Yeah, I'm just comparing it. So if 3 takes 3 seconds, so for order N, if 3 takes 3 seconds, 6 would take 6 seconds. Like it doubles and it doubles. For order N squared, if 3 takes 3 seconds, then 6 would take 9 seconds. So by doubling the data, I'm squaring the result, the cost of the result. Yeah.
Yeah. Okay, cool. It's so hard without graphics.
Yeah, it is. Pictures help. And fundamentally, like this is it's unfortunate. This stuff comes up in interviews because you being conscious of it allows you to make decisions like, oh, I should use a tree algorithm here. But to Mr. Shiny's point, there's a lot of times where the answer is just brute force it, right? Like the amount of time it'll take you to write a fancier algorithm. Like if I've only got 5 things in a list, screw it.
Yeah.
I don't care if I can shave 2 nanoseconds off.
It's going to take me so much longer to write it.
And I might make a mistake and all the rest of that kind of stuff.
Right.
And that's without getting into things like your processors have caches on them, which changes a lot of the behavior of this stuff underneath, right? So my preference, generally speaking, when I'm after performance is take a first pass at an algorithm, test it, use that to figure out what needs to be improved, and then improve the parts that need to be improved and ignore everything else. Because guessing ahead of time generally is a waste of time.
The other thing that I think is funky is that the code examples for Go, I'd never read Go. It looks like a mix of JavaScript and some other things with the semicolons in it, but there's a walrus style kind of operator. I'm guessing it doesn't.
It's not. It's assignment. It's assignment.
I'm pretty sure colon it's equals.
I think it's like Pascal. Yeah.
Okay. Interesting. Okay, cool. All right. Well, I think that takes us right into projects. My project is kind of more of an announcement. It was something that we saw as an article, and I thought, it's still kind of interesting, generally a project. And I always like to give resources for people to be able to play with data. I found another one today. I did an interview with a couple guys who did a book about pollers, and they gave me some other resources for people to explore. So I'll save it for that. But Google announced the general availability of a new Python client library for something called the Data Commons. And it's based around a V2 REST API. I was not aware of the Google project Data Commons. Their mission is to organize the world's publicly available statistical data, making it more accessible and useful for everyone. It's partnered with ONE or one.org, which is a global organization working to create investments needed for economic opportunities and healthier lives in Africa. The data also is coming from United Nations, which is interesting. So there's a bunch of partners here and some other universities. And it seems like Google is basically using Data Commons as a platform to house data and make it available through a variety of methods. One of the ways is an API, which you can then now use with Python, which is nice, or you can download the data, which usually will come in the form of a CSV, and you can kind of do a little bit of work there. A Python library makes it very easy to perform common queries against Data Commons, such as exploring the structure of the knowledge graph, retrieving data that's any of the 200,000 plus statistical variables from over 200 data sets and domains such as demographics, education, energy, environment, health, and housing, easily mapping entities from other data sets to entities that are inside Data Commons. And then the version 2 of the client library offers a bunch of technical improvements over version 1. It includes Pandas data frame API. They're supported as an integral module with single installation package and allowing seamless use, and then several other convenience methods for common data queries, API key management, integration with Pydantic libraries, improves the type safety and validation. We've talked about Pydantic quite a bit on the show. Support for multiple response formats, including JSON and Python dictionaries and lists. So a whole bunch of stuff here. I went and just looked at the website for Data Commons, and it's actually kind of fun to just kind of look around. Like, I know Kaggle is out there. I like how a lot of this data is organized. One of the ones that came up as quickly as I was searching is United States, who has no health insurance, which population without health insurance in counties in the United States, which is rather interesting to think about today as I'm recording this. So if you want to, you can download data from it, or again, you can access it through this Python API. So again, some more resources for you to, if you're interested in playing with. We talk about so many of these data science tools here, but often one of the questions is like, instead of just generating fake data, maybe there'd be some data you could play with and try out visualizations or try out some of these other techniques and, tools like polders and so forth. So a new resource for data. What do you got?
My project this week's called smartypants, and it's by Justin Mayer. It's a port of a similarly named project in, I think it was PHP. Its purpose is quote translation for HTML strings. So when you type a single or double quote on your keyboard, you get that straight up and down version. Frequently in typesetting, you instead want the curved quotes, which are paired with like a left and a right curve surrounding the thing that you're being quoted. These kinds of quotes are often called smart quotes, and a lot of word processors automatically replace your dumb quotes, for want of a better term, with your smart ones. So smartypants is both a command line script and a Python library. It essentially takes text, examines it for the normal dumb quotes, and then turns them into the smart variety using HTML character entities. So those are the ampersand, whatever's for the proper forms. It also handles N and M dashes. Those are elongated dashes used to separate thoughts in writing in case you want to look like you're an AI.
Yeah, that's what I've been hearing.
There were several threads recently about the fact that AI uses M dashes more frequently than normal people. Yeah. And then a bunch of Pythonistas spoke up about how much they love M dashes. It was a thing for about 10 minutes. Anyway, if you wrote down that run-on sentence I just said, if you wrote it all down, what I spat out, you would have several M dashes in it because there were tangents in the tangents. Anyhow, in addition to that, it also handles turning ... into the ellipsis character. The library is smart enough to skip over text inside of certain HTML blocks. So if you've got code tags, for example, it will not translate them. It'll assume they're verbatim. So this is a very specific kind of library.
Yeah.
But like with all very specific kind of libraries, if you have this problem, it saves you from dealing it with yourself. So take a look at it if it's helpful.
Yeah, I think it might be interesting as one of these sort of smaller projects where you can really read through it. If you're looking for something like that as an example project to say, oh, how did this person attack this?
Yes.
There's a whole area about symbols in there, which I think is interesting too. So yeah, cool. All right, Christopher. Well, thanks for bringing all these articles and projects this week. And it is the summer, so I guess we'll keep the requests going. I'll have a link for people to submit stuff to PyCoders. But yeah, thanks for coming on the show.
Always happy to be here.
I want to thank Christopher Trudeau for coming on the show again. And I want to thank you for listening to the Real Python Podcast. Make sure that you click that follow button in your podcast player. And if you see a subscribe button somewhere, remember that the Real Python Podcast is free. If you like the show, please leave us a review. You can find show notes with links to all the topics we spoke about inside your podcast player or at realpython.com/podcast. And while you're there, you can leave us a question or a topic idea. I've been your host, Christopher Bailey, and I look forward to talking to you soon.